Yeah, as you said, I'm Rob Steenberg. I'm a space weather forecaster and scientist at NOAA's Space Weather Prediction Center in Boulder, Colorado, where we've been producing public space weather forecasts since 1965. Um, they get out a lot differently than they used to. Some of them used to go out by telegram, believe it or not. But anyhow, I ended up there in 2007 because I was in the Air Force, and I was given the choice of a second tour in Baghdad or an opportunity to go to graduate school. And I'd been to Baghdad already, and I said, you know what, I'm going to try graduate school because they probably won't kill me there. And they still tried, but just differently. It was not mortars, it was homework. But in any case, I survived that and ended up as the Air Force liaison to the Space Weather Prediction Center. So NOAA's center there in Boulder is the nation's official source for all the watches, warnings, alerts, advisories, and so on that are produced for space weather. We handle the civilian side of things. Now, there's a similar function in Offutt Air Force Base in Omaha, Nebraska, and they do all the military stuff. And the reason we have a liaison is so that we're all on the same page when it comes to these events, because ultimately we all report up the chain of command of the same individual. So we want to make sure we got our stories straight. So that's a little bit of an introduction just for on the ham side of things. I got licensed in 1980 when I was a freshman in high school. My metal shop teacher was the faculty lead for the radio club there in my high school back when we had radio clubs. And yeah, I got interested in it because of tornadoes. I spent part of a day under a workbench in the basement of my father's house in 1974 during a super outbreak of tornadoes that hit across the United States, including Xenia, Ohio, which was southwest of where I lived. And I got hooked. That's how I got hooked on weather, and then I got hooked on ham radio because of the Skywarn stuff. So I ended up getting my license, and it turned out I really like Morse code. So that's why I have started collecting these bugs. All right. Well, I was asked to do an update on Solar Cycle 25. So I'm going to try and do that. Get things arranged here on my desktop. I got lots of windows and 2 screens, so I can get everything situated here, and then we'll hit the road. I should also mention, I think I saw him on here, another one of my NOAA colleagues, Sean Dahl, has joined us tonight. Sean doesn't have a call sign yet, but I'm trying to convince him, trying to bring him into the fold. He is at SWPC, our new service coordinator. And for those of you who participated in any of the either Skywarn activities or anything with the Weather Service, he's our equivalent of a warning coordination meteorologist. So he was kind enough to join me tonight. I've been doing a little proselytizing. So, all right, I think I'm situated. Let me get the presentation up here. Oops, you don't want to see my email. There we go. And see if that works. All right. So here's a Solar Cycle 25 update. And these photos, because I always wait till the last minute to put these things together, are from today. So these are 3 images of the sun. On the far left is a hydrogen alpha image. This is one of the ways we look at the sun, one of the wavelengths. And this is taken from a ground telescope. This particular telescope is in Chile. And you can see different features on there. The bright white areas are called plage, and you'll find sunspots around those sometimes. And the dark lines on there, the linear features, are called filaments, and that's another solar feature we keep an eye on. And then in the middle image, that's a 195 angstrom image. And that shows us things like that dark zone up at the top there, is called a coronal hole. Those are origins of high-speed solar wind streams that are higher than the normal solar wind that we usually experience, around 300 kilometers per second. And then finally, on the far right, you can see the active regions all lit up brightly there. So those are those plage areas you saw in the other photograph, and sunspots, and those are areas of lots of magnetic upheaval and energy. All right, so one way to give you a feel for the solar cycle is this awesome movie. Now, I'm going to have to do two things. I'm going to have to make sure the sound's off because it's got a great song, but I speed the movie up too, and then the song just sounds crazy. So let me get this going. Looks like I got the sound off, so I'm going to scoot us forward here to about a minute and a half. There we go. So between 2019 and 2020, we were in solar min. But now things start to take off. So here we're looking at the graph on the right shows the number of sunspots, and then the image on the left is from the GOES spacecraft. So you can see the active regions in the northern and southern hemisphere beginning to appear as we start to ramp up. Similarly, as the sunspot number is climbing, most of you probably know that the F10.7 centimeter flux is also rising. And that can be used as a proxy when you don't have the sunspot number because it follows the solar cycle as well. And that's really the number a lot of amateurs follow to see what the propagation might look like. So you can see we just keep heading up. So by 2022, we're already up to sunspot number 50. And when I looked at this earlier, it struck me that it started out looking like the southern hemisphere was the primary focus of activity, but you can see some as well in the mid-latitudes in the northern hemisphere starting to show up as well now. We number and follow each of these spot regions, and depending on their structure, their magnetic complexity, and their size, we'll assign a flare probability to them. So the solar flares you'll see here shortly are what jazz up the ionosphere, and in some cases create radio blackouts or at least degradation on certain frequencies. But there's a payoff afterwards because you have a slightly more energized ionosphere, which aids in propagation. So we stare at this for hours every day, among the other duties that we have. But this is how we track this stuff, and you can see we really start to take off now in 2023. And if you've been on the HF bands, you probably are aware. I see some great reports of activity on 28 megahertz and 21 megahertz, where normally, I hadn't seen a whole lot on there, but it's picked up quite a bit. And now you can see, things are rocking and rolling there. So we're having flares, we're having what's called coronal mass ejections, or big blobs of plasma ejected from the sun. And that keeps us pretty busy. So that's the solar cycle progression in a real quick fashion. Oops. All right, and then this is just an example of two plots. On the left is a sunspot number. And you can see the red line was the prediction that we made at the beginning of the solar cycle back in around 2019, 2018, 2019 timeframe. And this consensus prediction, which brings together experts from around the world, actually ended up lowballing what we have experienced so far. So you can see we're predicting a peak just over 100 around 2025, but things are ramping up and ramped up much more quickly, which was great news for us if you're an amateur and you like to get on HF. Now, I wanted to show you a beautiful new chart that our solar physicists made. Excuse me. And unfortunately, it's not allowed to be released yet because it still has to be approved. But once it's approved, it'll be out there on our webpage. So the updated prediction, which I can tell you right now, is a maximum sunspot number between 173 and 137 on the low end. It's happening sometime between January and October of 2024. So peaking a little earlier and higher than we had originally forecast. And then a maximum F10.7 centimeter flux of somewhere between 165 and 194. And here on this chart, you can just see it in comparison to the previous solar cycles dating back all the way to the 1700s. So you can see it's kind of an average cycle. It's a little better than last time. Cycle 24 was kind of really, really low, but definitely not the lowest. All right. Now, we're not the only ones in the solar cycle prediction game. There's a gentleman named Hathaway at NASA, and I think he's at Marshall Space Flight Center, and another solar physicist named Lisa Upton. They made a joint prediction, which you can see here. They're looking currently, their revised prediction is for a maximum sunspot number of 179.9, happening sometime in September or October of next year. And these are just some other plots that they produced. This is a picture of the sunspot area coverage from the 1800s onward. And you can see a trend as time goes. And this is something that we look for at the Space Weather Prediction Center. We kind of track, notice how early in the cycle the sunspots form more poleward, north and south of the equator. And then as time wears on, they start to converge towards the equator. And we'll see that migration, but it's really nice to see in images like this, which this type of image at the top there is called a butterfly diagram.
And Rob, I'm sorry to interrupt, but is this skewed at all by advances in technology and our ability to detect stuff? Or
yes. Well, they try and account for that. And so there's a group in Belgium at the Royal Observatory in Belgium at the Solar Influences Data Center, and they are the world maintainers of the sunspot number. So they are the official keepers of the sunspot number. They make the decision about what it is at the end of each month, and then they go back over the records. In fact, a few years back, they went through the entire record of sunspot numbers and did some recalculations. And I talked to one of the gentlemen who was involved in that project, and he said you can actually, after a while, because he looked at this for so much, he said you recognize particular observers because, you know, they had eye problems and things like that. And so he actually, after a while, would know who was on duty recording those sunspots just based on some of the characteristics. But yeah, that's something we have to worry about, and something we have to kind of account for. Improvements in technology over time. Now I have an observatory in space, a satellite called the Solar Dynamics Observatory, and I can see things particularly in some cases before the ground observers do, because they may have bad optical conditions, you know, cloud cover, things like that. So I'll pick up spots, and I may see spots that they'll never see. And so we have to be careful about numbering those particular regions. So we work together with the observatories to make sure that when we do number a region, it's one that's significant enough and going to stick around. But we won't always see all of them. And see, that's the very small ones can come and go fairly quickly, even during a 10-hour shift.
Well, has the period been consistent through all this time?
Pardon me?
You know, the period is somewhere around 11 years, right?
Oh, yeah. No, it has not. On average, it's 11 years, but it varies. We've seen it as long as like 14 years. So that varies as well. But on average, it's around 11 years. And the interesting thing is why that happens is still a mystery. They're understanding more through different techniques, like one is called helioseismology, and they're trying to understand how things flow beneath the solar surface, which the way the sunspots converge towards the equator there as the cycle goes on. They're looking at meridional flow. So they're trying to develop models of the sun to better understand, why it goes through the cycles and what affects their length. But there's a lot of open questions, which is one of the reasons it's very exciting to be part of this field. All right, next on the agenda, this is just another butterfly diagram, but here we're looking at the magnetic field. So you can see how the poles, the positive in yellow and the negative in blue, flip with each solar cycle. And one of the things we look for is that as to bring a solar cycle to the end is that complete reversal of the field. But this is not a particular diagram that we look at daily, but it is nice to kind of look at periodically just to see kind of where we are. All right, there's another prediction by a gentleman named Scott McIntosh, and he worked with another couple of collaborators using a different technique that's fairly cutting edge, and they came up with a maximum sunspot number of 184, and sometime between the fourth quarter of this calendar year, and the fourth quarter of next calendar year. And so you can see their prediction there. The original prediction from the consensus panel is there in the blue below the red one. And they've modified this a couple times. This is something that, the more data we have, the better we try to do with the prediction. All right. So why do we care? Well, the ionosphere is really for HF communications, and really communications even above HF. If you're working satellites or the space station, the ionosphere is where it's at. So here's where you have plasma density high enough to affect radio wave propagation, but the neutral atmosphere is still dense enough to influence the plasma dynamics and photochemistry. So the ionosphere is a really complex place. You have dynamic things going on as well as chemical things going on. And all this dynamics and chemistry, and then add in some magnetism, makes for a really interesting place. Overall, we're just looking for energy from radiation penetrating our atmosphere based on its initial energy and available absorbers. It'll interact with the atmospheric constituents, throw off electrons, ionize the ionosphere. And then the shape of the electron profile as you go up vertically is a result of the different production and loss mechanisms. And those production and loss mechanisms involve things like chemistry and dynamics. I couldn't have a talk about the ionosphere and propagation without at least one page full of equations, but I'll keep it brief here. It all boils down to the index of refraction. Depending on the frequency that you're transmitting with and the plasma frequency, which is a function of the electron density, your index of refraction will change. And so as the radio wave enters the ionosphere and encounters an increasing electron density and a decreasing index of refraction, it will actually bend the radio wave back towards Earth. Now, if the frequency is above the plasma frequency, it's going to penetrate the ionosphere, and that's how you talk to satellites. So there's a maximum frequency that you can use without penetrating the ionosphere. And there have been tools developed called ionosondes and digisondes that probe the ionosphere by shooting radio waves into it vertically across a broad spectrum a broad range of frequencies, and then capturing that data to produce the electron profile that you see on the right. So if you assume what's called a fixed takeoff angle for a particular antenna, the radiation pattern and the angle that the waves will interact with the ionosphere, higher signal frequencies require greater electron densities to cause reflection. And that means they'll penetrate higher into the ionosphere. So lower frequencies, conversely, will reflect at lower altitudes. And if you get high enough frequencies, they'll pass through the ionosphere, as I mentioned earlier. And those are just some relationships there between plasma frequencies and the electron density. And that electron density is going to be important when we start talking about space weather influences. Now, the other thing we need to keep in mind is radio waves can be absorbed. The absorption's at a maximum where the density and the collision frequency peaks. So the collision between the particles and higher density are directly proportional to the absorption, and it's inversely proportional to the square of whatever frequency you're using, which means generally you're going to try to use the highest possible frequency that you can without penetrating the ionosphere to avoid signal degradation. And we typically call that the maximum usable frequency. The chart that you see there with the big red bullseye is an example of a X17 flare. So the flares are rated in levels from C for common, M for moderate, and X for extreme. So this is the most extreme type of flare, and an X17 is extremely extreme. So that's why you're looking at a big radio blackout over Africa. Now, that term radio blackout, we've learned over the years, is kind of a misnomer, because whether or not your radio signal is completely obliterated depends on a lot of different variables, which you'll probably be familiar with, like your transmitter power, your receiver sensitivity, the type of communication mode that you're using. All those things come into play. So strictly speaking, it's not necessarily a radio blackout for everything. But some particular types of transmissions and power levels and receivers would be affected and completely obliterated, while others may still be able to make the circuit. This was from an episode in last solar cycle in 2017 on September. We had an X2 and an X9 flare. What I've plotted on the x-axis is your time. On the y-axis are the connections recorded in the week's signal propagation reporter for those various frequencies. So if any of you are familiar with the Whisper network, I just pulled that data down, and I pulled it down for the entire globe. So I didn't care whether it was the day side or the night side. I just wanted all the data. And then I looked at 14, 10, and 7 megahertz, and I looked at the number of connections between stations during those two flares. And you can see how it impacted all those frequencies to some degree. And then they all recovered. And the one thing I wanted to draw your attention to in this particular image was the impact that it had at 14 megahertz, because you ended up, after this flare activity, with an ionosphere that had higher, where you had a larger number of connections at 14 megahertz than when you started. And that's one of the consequences. You suffer a bit of degradation when the flare happens, but the payoff is, if you wait for a bit, you'll have a very energized ionosphere to work with. So the three types of space weather that we keep an eye out for at SWIFC and that could have an impact on you include the solar flares, and we have something called the NOAA scales. R is for radio blackouts. So the R scale rates from 1 to 5 the severity of that interference based on the magnitude of the flare. So the stronger the flare, the higher the R is going to be. It ranges from 1 to 5. You can kind of think about them like the hurricane scales, Cat 5 versus a Cat 1 hurricane. So the flares caused increased ionization and absorption in the D region, and they're going to increase the lowest usable frequency, because if you get too low, then you'll have absorption. The flares in general are typically around an hour. Some are longer, some are shorter. They have different characteristics. But like I said earlier, the absorption is followed by what I call the jazzed up ionosphere. So that can be a benefit. Geomagnetic storms, the G scale, that can bring noise and depress the maximum usable frequency. So the geomagnetic storms, as long as you have an isolated one, typically it's going to be about 24 hours of noise. And then you get something called a maximum usable frequency depression. And that's because of some things that happen with the ionospheric chemistry and dynamics that result in a depletion of electron density, and consequently a lowering of the frequency that you can use. And these depressions can hang around. They can hang around for 3 days. And there's patches, and they kind of move around the globe. So you may see that affecting an area at particular times. The key thing is, though, they're not ubiquitous. They don't blanket the entire Earth. Like I said, they're patches, so their effects will be localized. And then finally, we haven't really talked about it much, but space radiation storms can cause absorption in the polar regions, and those absorption phenomena can last for days because you get radiation in there, you get ionization, but it hangs around and can have a significant impact. This will actually cause airlines to divert their routes over the poles because of that lack of communications.
Does one or all of these happen to cause the northern lights?
So the northern lights are going to be a consequence of the geomagnetic storms. So when that happens, you have a big blob of plasma that's come from the sun. Now, it could be associated with a solar flare, so that'll kick it off. And in 18 hours to 3 days or 4 days, the blob of plasma will get to Earth. The blob has its own magnetic field that interacts with Earth's magnetic field. And the magnitude or the strength of that interaction determines how big the storm's going to be. And then you'll get field lines at the front, the sun-facing side of the magnetosphere that will break, and then they'll reconnect in the magnetotail, accelerate particles along those field lines back towards the poles. They'll crash down into our atmosphere, interact with the atmospheric neutrals, and produce lights. So that's the northern lights. So that's a consequence of the geomagnetic storms.
Are those also what knocked out telegraphy back in the 1800s?
Yes, that's exactly it. So we had a huge coronal mass ejection, very fast, got here very quickly. And that fluctuating magnetic field, when those two fields came together, you can think about like ringing a bell, but it was fluctuating so much that it was inducing current on those telegraph lines. And so the operators were able to operate without their batteries. In some cases, equipment was overloaded and caught fire. In modern society, we worry about the electric grid because those are huge conductors strung all across the nation, and all across North America, actually. And so we work very closely with the power companies so that they can anticipate these things and take actions to mitigate any impacts.
Thank you.
Yeah, we get on the phone, actually, and we call up the entire North American continent of power grid operators. It's called the North American Electric Reliability Corporation Hotline. And we talk to reliability coordinators across North America, and we tell them what's going on, and then they do their thing. And it's going to vary. What they do is going to vary by where they're located, because part of the equation has to do with ground conductivity, and that's not homogeneous across the U.S. There's hotspots, basically.
Do they believe your reports in Texas?
We don't. Yeah,
I'm sorry.
No, but what I was going to say is, in terms of the ground conductivity, we still have some holes in Texas. I think is one of the holes we have to fill. But so far, one of the what we found is the like the Appalachians. up through the DC corridor, that's all lit up. So that ground conductivity combined with the magnetic fluctuations is very potent in that region, as well as up in Minnesota and Wisconsin. All right. There. Here's a picture of the NOAA scales. You can get to this on our website. I've got our URL there. And what it does, it breaks down the different levels, what the nomenclature is, whether it's extreme or moderate or strong. It gives you a list of impacts. It gives you the physical measure that it's based on. For instance, X-ray flares are based on the X-ray flux detected by the GOES spacecraft, the same spacecraft that give you the weather satellite photos. And then the average frequency per solar cycle. And then we do the same for radiation storms and geomagnetic storms. So it's a handy guide. Keep in mind it's 23 years old. So it's based on older statistics. We're in the process, and it's got to be probably a decade-long process of updating these to be more relevant, because technology has changed in the past 23 years. And we expect it to continue to change. So we need to refine these impacts. And, we're not sure what it's going to look like when it comes out the other end. It might be totally revamped. Some scales may go away. We're not really sure. A lot of it really is just going to depend on feedback that we get from the people we serve. That's really the driving force behind these. All right, so for amateur radio, some hints. This came from Paul Harden, if you're familiar with the QRP Amateur Radio Club International. He did a talk one year, NA5N is his call sign, and he had propagation hints based on impacts from space weather. So major flares, seldom last more than an hour. Take a break. I usually go mess around on the workbench, solder something, wait for things to get better, or just go relax. But like he says the same thing, kind of jazzes up the ionosphere. So you get a higher maximum usable frequency. So immediately following a solar flare till sundown, and that can last actually into post-sunset, sometimes depending on how significant it was. Another hint he had was the magnetic field can get very quiet following a strong geomagnetic storm for about 12 to 24 hours. Great time to work on the low bands because the noise levels will be down. So once the storm ends, things get quiet. Now, the other side of it is for the higher frequencies, you remember you're going to have that maximum usable frequency depression after a geomagnetic storm. So that's a potential. On our website, you'll find the current K index. That's the most up-to-date number. That's going to be at a maximum 3 hours old because it's updated every 3 hours. You can get it on WWV or on the internet. And then the A indices just tell you what happened yesterday. So the A index is not going to give you as much information in the immediate sense as the K index. But if you had a terrible day on the radio the day before, you can look back and say, the A index was 400, or, well, that's probably too high, but yeah, high A index. All right, some final thoughts. Solar flux is good for HF propagation above 10 megahertz. That's why in Solar Min, I spent damn near all my time on 40 meters. Spent a lot of time there. The MUF seldom drops below 10 megahertz, which is why the low bands are always open. K index, we just talked about that. 30 meters is weird. I operate there. That was the first rock mite I built was on for the 30-meter band, and I had my best distance contact with a 0.5 watt. I talked from Houston, Texas to Hungary, which was amazing. But so it's weird, but I like it. Flares are different. Now the key thing is number 5 there on the bottom. Don't ever let reports of flares or geomag storms scare you off from getting on the air, because like I said, things like those MUF blobs, or those transients, are localized. You're not always going to see that. the flare could not be affecting the particular region that you're in because you're rotating into the night sector, for instance. And you can still take advantage of the gray line and stuff like that. So there's, always that. My thing is just always turn the radio on, listen around, call CQ if you want, see if anybody's out there, but never be diverted from getting on the air just because you hear about these things. Go ahead and check it out because sometimes it'll surprise you. I had the most contacts I've ever had in my life during solar minimum, believe it or not. So that was wild.
Bill Rinker, W60AV, has a question in the chat if you can see that, Rob.
Oh yeah.
Can I interrupt you just a second, Rob?
Yeah.
And we'll let Bill, and then we'll have a chance for questions. But just to remind everybody, the DRC members, I think, please, if you want to get it on the drawing, please go into the chat and get the link and get yourself in the drawing. So please do that if you so desire. Go ahead, Rob.
Okay. Let's see, Bill. Based on past solar cycle history and more. Oh yeah, there's absolutely a concern for another Carrington event. That's always out there. There have been different studies done to see like how likely is it, and I'm relying on my memory here, so there's some error bars associated with that. But I think the number I saw, the biggest number was like a 10% chance in the next decade. But don't hold me to that because, like I said, I'm dealing with my memory and there's wide error bars associated with that. But it's definitely a thing, and that's definitely why, from industry to government at state, local, and federal levels, they're all paying attention to space weather. And Sean can talk more to this because he's briefed emergency managers across the nation, and in fact, a national gathering of them even about this. They're interested in it, and they want to be prepared for it.
And Rob, can you explain what the Carrington event was?
Sure. That was in 1859. And what it was a significant solar flare. It's named for Richard Carrington, who was a scientist who studied the sun. He had his own observatory. He was watching the sun and making a sunspot drawing. And when the flare occurred, it was actually potent enough to produce emissions into white light, so visible light. So he saw it. So he's projecting the sun onto a piece of paper where he's making his drawing, and it lights up white. And he's like, never saw that before.
Wow.
So he got somebody else, I guess, close enough by who could also see it. And it was after that Carrington event, within, I think it was, the thing got here in under 24 hours. They saw huge aurora. The telegraph stations, as was mentioned earlier, kicked off. This was just a stupendous storm. I mean, it drove the northern lights down to Cuba. So they were kind of not the southern lights, but they were definitely closer to the equator. I read stories about miners in Colorado here actually getting up to go work the mines, thinking that it was dawn. And then, I don't really know, how they came to the conclusion that it was not, other than some guy looking at his watch and going, hey, wait a minute. But yeah, it was phenomenal. People on the East Coast thought whole cities were on fire because of the glow from these things. It was absolutely incredible. Now, fast forward to 2023, think of all the technology that we rely on, the satellites, the power grid, the internet, all this, and the impact that something like that would have. So that's why, I mean, it's gotten the attention of lawmakers on both sides of the aisle. They've passed legislation directing the space weather community, for instance, to provide benchmarks. What's the worst solar storm that could happen? What's the worst flare? What's the worst geomagnetic storm that could happen? What should we prepare for, and how likely is it? So all these kinds of things come up. Also, if you're interested, there's a book called The Sun King. It's about Richard Carrington, and it reads like an episode of Jerry Springer and Nova mixed together. So there's just absolutely breathtaking science along with adultery and stabbing. So it's an amazing book. Let's see. There's my next slide. All right. So here's some resources. Our website is www.spaceweather.gov. And if you'd like to learn more about radio wave propagation, there was a presentation put together by the folks at the University Corporation for Atmospheric Research, or UCAR, in their MET-ED, or Meteorological Education Program for the Navy, that deals with radio wave propagation. So that's a pretty handy thing. And then finally, I'd be remiss if I didn't show you some awesome pictures that Sean took. And I hope, Sean, that you don't mind that I added these to the presentation. But Sean's hobby right now is beyond the ionosphere and actually beyond this solar system. He takes these phenomenal photographs with his telescope. And but I'm still trying to convince him to get into radio. So I'm relying on you guys to help me.
Thanks, Rob.
And that's it. That's my presentation. And I'm open to questions. And Sean, if you want to add anything, please chime in.
Yeah, I don't have much to add, Rob. Thanks. This is good education for me, too, learning more about ham radio. But yeah, Rob mentioned it. Emergency management is getting very interested in space weather for good reason, because they realize that it can impact things, not just technology, but their ability to communicate during a crisis of some kind, usually in combo with something else. So I'm learning things right now about what their needs are to that. I was talking to a county in Chicago that covers Chicago, and in their urban environment, apparently they have a concern with HF radio because their repeater system, I don't know if I quite understand yet, but I think there's some kind of backup system with their repeater system to get around, you know, the towers and skyscrapers and thing to communicate during a crisis. So they have an interest in HF radio, which totally surprised me. I didn't think that they would in their location. But yeah, this is always a growing thing for us to learn and for the users and end customers to be aware of, and that way we can have a better working relationship. Thanks.
Thanks, Sean. Yeah, one thing oh. Oh, awesome. Well, thanks. Yeah, the thing I was going to say is, you know, you think about space weather, the only visible manifestation of this phenomenon that we have are the northern lights or the southern lights if you're down in Australia. But, you know, that's really it. In your day-to-day life, nobody's out there dodging protons or being blown over by the solar wind, right? But the impacts will all be kind of cascading things. You know, if we have a power outage induced by a geomagnetic storm, the effects, the consequences, and you saw, actually you mentioned Texas earlier, you saw this when the grid went down in Texas during the winter, during that storm. You know, very quickly you can see impacts from this. But those are not direct effects. You know, they're kind of the indirect effects of a space weather event. You know, at some point, they won't be able to pump water anymore or gasoline and those kind of things. So, you know, that's where the impact comes from. Most of it is not direct, like getting hit with a 3/4 inch hailstone on the head. All right, and then somebody had mentioned earlier bugs. So there's my current bug collection. That one on the far right I ordered from Vibraplex. That's an older one, but yeah. So there's my bugs.
How do you use one of those things? I mean, just get used to it counting the gets really fast for you, or?
Yeah, I mean that. So for me, I see this one on the far left. See that big extension and that weight at the end? So that pulls the speed down to something manageable for me, like 15 words a minute or less, at least starting out, because my hand-eye coordination, my hand is just not that good yet. And so I have to slow things down. And yeah, you just get used to the dits, and that you have to remember to make the DAWs manually. And that's been the hardest thing, because I'll go CQ, you know, it'll be like da-did, da-did, da-da-did, ah. You know, lay on there, and so it's been a learning experience, but I'm having a blast. I mean, these things are fun. So I've made 15 contacts over single sideband in my 40-some year career on the airwaves, but so I'm over a dozen now.
Okay, any more questions for Rob? Last reminder for the drawing. How many we got, Jeff?
8 so far.
8. Last call. Anybody want to get in there? DRC members, go to the chat. And while hopefully somebody else is doing that, thanks so much, Rob. Very interesting. Very, very good.
All right.
And
Well,
thanks.
thanks.
I like your keys there. The bugs, that's my favorite. I've got straight keys. I've got bugs. I've got a coffin key and so forth. But my favorite right now is a 1947 Vibraplex Champion, and I really like it. So anyway,
Nice.
great.
All right. Well,
Okay.
see, you should have told me that. Now I'm going to be showing up at your doorstep saying, "Hey, let me lick those keys." But
There's some,
well,
there's
hey,
some
it was.
kudos in the chat there, Rob, if you want to see them.
Oh, yeah. Oh, thank you.
So we still holding at 8,
Excellent.
Jeff?
Yes, we're still at 8.
All
I
right.
guess that I
Come
think
on.
they've had ample chance. So the
Yeah,
odds are tremendous there for you.
you got
So
12, right?
All right.
pull the trigger, I guess, and we'll send everybody home.
All right, I've randomized the range, and our winner tonight is Fred, AE0RK.
NE0RT. Well, congratulations, Fred. Kathy will get a certificate off to you in the next day or so. NE0RK. NE0RK.
Alpha Edward 0,
Oh, AE.
Romeo King.
AE0RK, Fred. Okay. All righty. Congrats, Fred. Well, if there's nothing else or any questions or comments, I guess we'll put a lid on it for tonight. Thanks everybody for coming. We'll get more information out on the holiday party, but keep that in mind. December 20th up at the old, it's still Jeffco Airport to me, but Rocky Mountain Metropolitan in the main terminal building. So what do you got a hand there, Peter? Go ahead,
Yes.
Peter.
Yes, thank you. Slightly off topic, but maybe of interest. This Saturday, Edge of Space Science will launch a weather balloon out in Deer Trail. If you want to look on the website, eoss.org has the information about the balloon number 347.
And I'll be there. I'm going out with Jim Langstead.
Okay, I'll see you there.
You betcha. Anything else?
Just to decode the acronym, it's Edge of Space Sciences. I don't know if Peter said that or not, but EOSS.
EOSS.
Yep.
Yep. 300 and how many? What's this flight? And
347.
347 launches, and to my knowledge, they've never not recovered one in that many launches. Some of them are pretty difficult, but they're persistent.
It's an amazing record. I'm sure they saw a lot of windmills and cows.
Yeah. Rain and snow and wind and cold. And it's a lot of fun.
Yep, my first one. I'm looking forward to it. So you can teach me all about it.
Okay. I usually help them gassing them up, so I'll be around the trailer typically. It's a nice facility out there. We meet at the school there in Deer Trail, and they open it up so you can go in and use the facilities and so forth before you get out of there. So it's a great time. Anything else? Hearing nothing. Good evening, everybody. And again, Rob, thanks so much.
All right. Thank you. It was a pleasure. Take care.
Educational.
Bye.
Bye-bye.